Hello, my name is Bob Barnett. I'm a historical technologist. I'm also a life senior member of the Institute of Electrical and Electronic Engineers and a retired professional engineer. In this video, I'll show a couple of examples of how historians got technology wrong. I'll also suggest that a discipline is needed to treat the technology of history as opposed to just the history of technology. We'll start with Nikola Tesla. He's probably the best known. Although there are many books attributing to Tesla the invention of fantastic devices that contravene the laws of physics, we'll look at an everyday example important to life as we know it, the induction motor. Then we'll look at another techno-guru, Frank Sprag, who is famous for his installation of a streetcar network in Richmond, Virginia. There are other examples, for instance, James Watt, who didn't invent the steam engine. There's Henry Ford, who didn't invent the assembly line, and Thomas Edison, who didn't invent the electric light. Often these people had a legitimate contribution to technology. However, they frequently have been attributed accomplishments they did not deserve. In a small number of cases, this was a result of the particular inventor or engineer being a self-promoter. But frequently, it was a result of the historian's lack of technical knowledge. So, how could this happen, you may ask? The problem is that most historians are not trained in technology, not even a little. They have a somewhat abstract view of the systems they write about. In the best cases, they approach demuth in their depiction of the processes. What they need is a Sheeler-like understanding. First, we'll look at the problems in some detail, and then we'll try to come up with a solution. We'll start with a brief bio of each of our chosen victims. This biographical sketch is based on Christopher Cook's book, The Truth About Tesla. Tesla was born in 1856 on the stroke of midnight between July 9th and July 10th. Born during a violent electrical storm, his mother said that he was not a child of the storm, but a child of light. He seems to have had the marketing gene passed to him from his mother. Tesla attended the Joanneum Polytechnic Institute in Graz, Austria, that had no official electrical course. This is not surprising, since that particular discipline would not officially emerge until several decades later. Most of what Tesla learned about electricity he received from a mathematics professor, Jacob Poschel. Eventually, Tesla found work with an Edison subsidiary in Paris. He soon realized that since Edison's system was a direct current one, there was no interest in alternating current. Tesla transferred to the Edison shops in New York City, where he was introduced to Alfred Brown. Brown was head of Western Union Telegraph in New York City. Brown and a New York City lawyer named Charles Peck were persuaded to fund a lab for Tesla. They called it the Tesla Electric Company. In 1888, Peck and Brown traveled to Pittsburgh to try to interest Westinghouse in buying the Tesla patents. The total price would have amounted to over $250,000 over 15 years. Empires of Light is a good example of the Tesla problem that infects even well-educated historians. Jill Jones is a historian. She is the author of several books, including South Bronx Rising, The Rise and Fall and Resurrection of an American City, and Empires of Light, Edison, Tesla, Westinghouse, and the Race to Electrify the World. She has been a National Endowment for the Humanities Scholar and received several grants from the Ford Foundation. Jones graduated from Barnard College with a BA in 1974 and Columbia University with a Master of Science in 1977. She also graduated from the same university with a PhD in 1992. Even though she had a rather down-home narrative style, Jones's information is generally accurate, with one glaring exception. I think that this highlights the need for some technical background, if not with the author, at least with the research assistants. This is particularly evident when dealing with Tesla. On page 289 of Empires of Light, she writes, "At the mill, the electricity was stepped down to power a 100 horsepower single-phase Tesla motor. The question was, would it run reliably? So all that summer, fall and winter, and all through 1892, the Westinghouse engineers were delighted as the simple power system and the sturdy motor hummed steadily along. The Tesla AC system had passed its first real job with flying colors." This statement is untrue in several respects. According to Jones, she was taking her info from a paper by Charles Scott. She says that it was published in the Electrical Engineer, June 5, 1892. It appears that was no such article, not at least in the publication she cites. She is likely referring to a paper with an identical title and date that was published by Scott in the American Institute of Electrical Engineers Transactions of June 1892, shown here. Although the page number does not appear on the first page of the article, it is actually page 425. Here, on page 430 and 431, Scott, who was an engineer with Westinghouse at the time, identifies the plant he is talking about as being located near Telluride, Colorado, and owned by L.L. Nunn. In this plant, a Pelton wheel turbine drives an alternating current generator. The current from the generator drives an alternating current synchronous motor of 100 horsepower. On page 431, we are shown a wiring diagram for the setup. On the left is a synchronous generator, or alternator. On the right is a synchronous motor. To the left of the synchronous motor is a Tesla motor used to start the synchronous motor. Scott says that a synchronous motor requires an auxiliary starting device. That's what the Tesla motor was used for, and not as a means of driving a mill load. He continues that this motor comes up quickly to the normal speed and then has ample capacity for bringing the armature of the large motor up to speed. The large motor is then excited and runs as a self-excited alternating current dynamo. The small motor is then switched off. Although Scott says that the Tesla motor has ample capacity to perform its synchronizing function, he was an employee of the Westinghouse Company at that time and might well be expected to say that. An article on page 176 of Cassier's magazine, January 1905, by P.N. Nunn, one of the mine owners, has a different story. He says that the main motor was brought up to synchronous speed by a single-phase induction starting motor, which received its current at full line voltage. The current taken by the starting motor was more than the full load current of the main motor. This starting motor even required starting by hand, its torque being zero at starting and so feeble at low speeds that when cold it could only with the greatest difficulty be persuaded to pull up to speed its belt and loose pulley. It's clear from these two articles that this was not the proving ground for the Tesla motor. It's understandable that anyone with no technical training who thinks erroneously that Tesla invented AC might make this mistake. Frank Sprag was born into a large family in Milford, Connecticut on July 25, 1857. He was one of 10 children. Because he showed an interest in science and mathematics, his high school principal suggested that he apply to the United States Naval Academy. Sprag was accepted in 1874. During this time, he developed an interest in electrical theory. He also attained a propensity for the use of hands-on trial-and-error method of solving technical problems. Although this aspect of his personality is held up as an attribute, this trial-and-error method would not serve him well in Richmond, as we will see. Sprag graduated from Annapolis in 1878. Sprague's interest in electricity led him to resign his naval commission in 1883 and take a position with the Edison Company. Sprag wanted to focus on motors, but found himself in a firm whose prime interest was incandescent lighting. Edison put him in charge of construction of power plants, and although he performed well, Sprag did not lose his interest in the development of electric motors. He left Edison in 1884 and started his own company, the Sprag Electric Railway and Motor Company. In 1887, Sprag began the construction of a trolley car system in Richmond, Virginia, that was less than successful. In 1892, he established the Sprag Electric Elevator Company and developed a system that was installed in 1894 in the Postal Telegraph Building in New York City. But he probably should be best remembered for his multiple unit control system, a variation of which is still in use on subways and diesel locomotives to this day. William D. Middleton was a licensed professional civil engineer and a respected writer of transportation technology with several traction books published. These books include The Interurban Era, 1961, North Shore, America's Fastest Interurban, 1964, and When Steam Railroads Electrified, 1974. In 1950, Middleton earned his undergraduate degree in civil engineering from Rensselaer Polytechnical Institute. From 1950 to 1979, he was an engineer with the United States Navy and retired as a commander. After retiring from the Navy, he served in the position of Chief Facilities Officer at the University of Virginia. From the 1950s until 2011, he was an active railroad historian and a writer who published over 20 books with numerous magazine articles. Unlike Jones, Middleton wasn't a trained professional historian. Although Middleton's book, Frank Julian Sprag, did a good job of laying out Sprag's career, the part that deals with Sprag's motor problem on the trolley line in Richmond, Virginia, has some inaccuracies. Middleton is not alone in this respect. Others have made the same error. Before we look at where Middleton went off the rails, we'll look at what Sprag did in Richmond. Sprag believed that a constant speed motor would be best for trolley service. He had been writing about such a motor from his earliest work. His patents of the late 1800s show this as well. U.S. Patent 315179, 7th of April 1885 says, with any given potential at the armature terminals, a constant speed may be maintained under varying loads by varying the strength of the field inversely with the variations in the load, so that when the load diminishes, the counter-electromotive force is increased, whereby the speed remains the same, and vice versa. In his 1934 AIEE article, Sprag, Digging in the Minds of the Motors, Transactions of the American Institute of Electrical Engineers, May 1934, page 697, he says, our initial industrial motor development was based on the important fact that on a constant potential circuit, the mechanical effects, variations of speed and power out, of a motor could be controlled by inverse variation of the strength of the magnetic field to determine the differential of the line and motor electromotive forces. Also, with two magnetizing fields, one of high resistance across the line for the main field excitation, and another of a few turns in opposition to it and in series with the armature, it would be possible for certain proportions to operate a motor at the same speed under varying loads. The shunt motor does not have a constant speed characteristic. Its speed decreases with increasing load torque. This is referred to as a drooping load characteristic. Drooping means that as the torque required by the motor's load increases, the speed drops. This is the mechanism by which the motor takes on load. A decrease in speed would allow more current to be drawn by a motor to produce an increase in torque. This increase in torque is required when climbing a hill. The operator typically used some sort of drum controller to reduce the resistance connected in the motor circuit, which applied additional voltage to the armature. This in turn supplied that additional torque needed to bring the car back to the required speed. The opposite was true when going downhill. This is known as armature voltage control and was the accepted method of speed control at the time. But Sprag wanted to automatically control torque to control changes in speed. Sprag was aware that James Watt had solved this speed problem by inventing a flyball governor. The governor increased or decreased the input of steam to the engine to hold the speed constant. In Sprag's U.S. patent number 295454, we see a controller that did the same thing, but with an electric motor. This patent is dated the 18th of March, 1884. We can see here a flyball set up on the top right side of the DC motor. The governor connects or disconnects portions of the motor's field in order to maintain speed constant. On page 40 of Frank Julian Sprag, Middleton says, Sprag's motors were well designed and incorporated several new features, and their merits were quickly recognized. The motor operated at constant speed, regardless of changes in the load. The figure shows the curves of a differential compound motor and a shunt motor. The differential motor has its no-load and full-load speed virtually the same. It is more or less a motor that operates at nearly constant speed. The problem with the differential motor is that, in order to keep the speed from dropping, it draws even more current than taken by an ordinary shunt motor. The hills in Richmond were the cause of this increased current that resulted in Sprag's brush problems. It was just a simple matter that, in effort to maintain a constant speed, the differential compound motor drew too much current. What was actually required was a series-connected motor. Benjamin Lammy, a Westinghouse employee, was responsible for the development of the series motor in traction service, but this was still a decade or two down the road. The series motor was, in many cases, still is, the traction motor of choice. Sprag himself was aware that things were far from perfect at Richmond. In his article in the Engineering magazine, April to September 1894, he wrote, "It was a daily occurrence to see a loaded car climb a grade with a lurid green glare lighting up the track. At about this time, $9 worth of brass per day, milled off the rough bars of the commutator, lined the track with a glittering path. Not a single trip was made without inspection, with generally a change of brushes or some other repair. But that was not all. Every armature was unwound, the body shortened, and then rewound. Disabled armatures were numerous, and to keep the road in operation, tons of machinery was shipped by express." Continuing, he says that gradually we saw our difficulties lessening, and little by little the number of cars in operation was increased. This gives the reader the impression that the problem was finally solved. Other biographers of Sprag have noted this motor problem, some haven't. Even so, most writers give the impression that Sprag eventually sorted out his motor problems. But an account by one of the Richmond superintendents, S. W. Huff, writing in the Cornell University's Sibley Journal of Engineering in October 1912, tells a different story. On page 2, Huff says that in 1890, the operators of the Pioneer Electric Railroad in Richmond, Virginia, had announced that after a thorough test, they were forced to admit that electricity as a means of propelling cars was a failure. On page 4, we read that there were times when only 1 or 2 cars were in operation and that field coils required constant rewinding. The motor problem often gets lost in the list of Sprag's important accomplishments. Nonetheless, Sprag's motors, the heart of his trolley system, were not a success. So assuming that a problem has been identified here, what's the solution? What sort of training would be appropriate for those who study the history of technology? This could be in the form of a 2-semester course at the technician level where math is simple. The goal would be for the student to understand the relationship between time, force, and mass with an elementary discussion on electric and magnetic fields. Without training along these lines, serious factual errors will continue to be made.